So what we'll talk about in this video is a little review of inverse functions and then a property of inverse functions that we can use to determine some ordered pairs that slightly change when we go from a function to its inverse. And this will help us answer some of the problems that we see in the first chapter of our calculus book. If you look at what I have graphed here, I have the graph of y equals e to the x, so that's up top, and then I have the graph of y equals natural log of x on the same coordinate plane. And these graphs, they're mirror images of each other, and whenever you graph a function and its inverse, as e to the x and natural log of x are, what's always going to happen with the graphs is they're going to reflect across the line y equals x. And what that means about each individual ordered pair is this point, 0, 1, is on the graph of e to the x. So on the graph of its inverse, a point that we'll see on it is going to be 1, 0. So essentially, when you reflect across y equals x, the x's and y's of each individual ordered pair are just going to exchange with each other, and that's how you get this other graph, the inverse graph, produced on the other side of this line. So just to kind of make sure that what I'm saying here does work, why don't we pick another point and use our calculator to kind of check it out here. So let's see, if we went ahead and we said, all right, what is e to the 0.5? So if I went onto the calculator, typed in e to the 0.5 or e to the 1/2, I get something, oops, and that's not what I was trying to type in. Let me try that one more time. If I type in e to the 0.5, I end up with that 1.65 essentially. So what this means is that on this graph right here, the top graph, when x is 0.5, right, we put that in place of x, we got a corresponding y value of about 1.65 if we just round that off. We can see the full display of that value here. Now, if we reflect this point across the line y equals e to the x, that should leave us right here, where now the y coordinate is 0.5 and the x coordinate is 1.65. Just to kind of make sure this is correct, our calculator has the capability to figure out what the natural log of this x value is. And if what I've been saying for the last couple minutes is true, we should see a value that's pretty darn close to 0.5. Don't expect it to be exactly 0.5 because we've rounded this value off a little bit. But if we went ahead and we, whoops, and that's the exponential again, I wanted the natural logarithm that time. If we type in the natural logarithm of 1.65, we should see a value that's relatively close to 0.5, and we definitely do. If we went ahead and we tried that one more time, and we included more digits of accuracy, so rather than rounding it to 1.65, if I went 487212171, I should see a value that's even closer to 0.5, and we definitely do see that. So when you have a function and its inverse, what always happens is that x and y coordinates always get exchanged with each other, and that's what happens when you reflect across the line y equals x. So if you look at this little chunk of problems from out of, let's see, I think this is section 0.3 of our calculus book. Why don't we look at number 14? 13 and 15 you'll be trying in the summer assignment, but if we wanted to try and do number 14 here, directions say assume that the function has an inverse. Without solving for the inverse, find the indicated function values. So if you wanted to find the inverse for problem number 14 here, let me just change the size of my pen there. If you wanted to figure out what the inverse is, if you said, all right, well, I've got this function y equals, so I'm just copying down the function that's written in number 14 or the function that's given in number 14. And what I'm sure a lot of you do remember doing in your last class is saying, well, if I want to find the inverse of this function, what I'm going to do is I'm going to exchange the x's and the y's, and then I'm going to have to try to resolve this for y. Now, the issue with doing that here is that you can't combine these. These two pieces both contain y's. This is a y cubed and that's a y to the first, so they're not like terms. You're not going to be able to resolve this for y. So the reason why the directions are kind of weird here, it says without solving for the inverse, it's because you can't do that. Although that would have been an option if we just would have had, say, an x cubed here, if this piece wasn't there, we could have done this the way you're a little more comfortable with. But what we're going to have to rely on to do part A and B here is we're going to have to really think about what we said on the previous screen, and that's when you go from a function to its inverse, the x and the y coordinates exchange with each other. So if we take a look at what this is saying right here, we want to know what f inverse, so the inverse of f evaluated at 1 is. So the question is this: what's going to go on that blank? F inverse of 1 equals something. Well, we can't determine that right away, but what we can do to kind of bridge the gap is we can say, well, if I go back to the function, what's going to happen is this y value, this output value, is going to become an x value or an input value, and this x value for the inverse is going to be a y value on f. So I've basically taken the x, made it a y. I've taken the original y and I've made it the x. So can you answer this question? Well, that should be easy enough, because all we're going to have to do to answer that is we're going to have to figure out when x cubed plus 2x plus 1 equals 1. And if you just kind of run through some values here, I think you're going to be able to run into this one quickly enough. If we did, try 1 if you're doing guess and checks. If we put a 1 here, 1 there, I think we get 4. So 4 doesn't equal 1, obviously. But if we put 0, what happens if we put 0 cubed plus 2 times 0 plus 1? Well, that is 1. That checks out. So that means when we put 0 in place of the x in f, we get a 1 as the output. That must mean when we put 1 in as the x for the inverse, we're going to get this as the output. So it's a little bit different, a little bit goofy. We're going to use this technique a little bit later on in the year in Chapter 2. When you run into problems in this little set here from out of Section 03, do what we're doing here. It's going to be a little bit of guess and check to try to figure out which x value on the function produces the y value, and then once you do that, you've found your answer. So hopefully that has helped.